All right, so the last time we met, we talked about cardinality. We discussed what cardinality is, why it's important. We also discussed the forms or the types of cardinality, the degrees of cardinality. Okay. We should know why we are doing whatever it is we are doing. We should always know why we are doing it. For cardinality, we know it's a design concept. It's supposed to help us in our design. But generally, because cardinality shows us the relationship of rows in one entity with rows in another entity, cardinality is our first step in understanding which entity would be the primary entity and which entity will be the secondary entity. Okay, so you should know that during your design, especially when you get to the logical design, you have entities, and you may have as many entities as that business will require. Then you start taking those entities in pairs, two at a time, and then you will be looking at the business rules and be trying to come up with what their cardinality is. Because by knowing what those cardinality is, you will know where to put your primary key in that pair, in that entity pair, and where to put your foreign key, right? So we talked about the degrees of cardinality yesterday. We talked about the one-to-one, the one-to-many, and the many-to-many, and we will just briefly go over it again today and see how we can put in more context so that we can understand exactly what we're talking about. So we said that cardinality is the numeric relationship between two relations, and it determines how many occurrences of an entity can be present on either side of the relationship. Okay, so we said the first type of cardinality we had is the one-to-one cardinality, and in this type of cardinality we said that an occurrence or an instance of one entity relates to exactly one instance of another entity. And because of this, we said that both of those entities have the same primary key. Okay, so you can see from the slide that we have here that we have two entities, the employee entity and the job role entity. We are saying that the business rule for this entity is, or in this particular business that we are trying to model the data, the business rule is that every employee can have one job role. That's the business rule. And because every employee can have one job role, and one job role can be associated with just one employee, we said that this is a one-to-one relationship. Don't forget that yesterday we said to be able to determine what the cardinality is, you need to consider the relationship in both directions. So you need to go from this direction to this direction, and then you need to traverse the relationship back from where you ended to where you started from. Okay, so both ways. So we said that an employee, so again, remember our conversation yesterday. We said in the world of cardinality, there are only two terms that are important. It's either one, or when it's more than one, many. Those are the only two things that you need to be cognizant of in cardinality. Okay? So in this case, we've been told that one employee can have one job role. Okay? So one employee can have one job role. All right, so what about job role to employee? Okay, again, one job role can be associated to one employee, right? And we said yesterday that we just take, on both sides, we take the largest. All right, so that's how we get to our one-to-one cardinality. Now, notice that we are still representing our entities with our rectangular box, but then you can see that the relationship now is, the relationship line is kind of different than what we've been having. Before it was just one straight line, but you will see that in a one-to-one cardinality, you would see that there are vertical bars on the one side. This is what designates in an entity relationship diagram that the cardinality is a one-to-one. Okay, so whenever you see these two vertical bars, that side is the one side. Okay, and we call this notation, where we use these symbols to represent the cardinality. In our own case, we call that notation the crow's foot notation. All right, it's called the crow's foot notation. You will see why it's called the crow's foot in a few minutes. But then just note that in your entity relationship diagram, when you are representing the relationship and the side that you are on is the one side, right? You have these two vertical bars across your relationship line. So because they are on both sides, if we see this particular relationship between the two entities, we know that it's a one-to-one relationship. Okay, so another thing to note is that both of the entities have the same primary key. Both entities have the employee ID primary key. So the employee table and the job role table, or the job role entity, they both have the employee ID, which, like we said yesterday, means that we could actually represent this relationship in just one entity. But there are times when, by design, we just decide that no, the employee table might have a lot of attributes, right? That joining or adding the job role attributes to it might make that table to become, or that entity to become, very wide, and we want to try to avoid a wide entity. So we just chose that, although we know that these two entities can be represented as one entity, but we decide that we are going to make them two entities just to make sure that performance in the database is optimal. Okay, so but just note that in a one-to-one cardinality, the two entities that we are talking about have the exact same primary key, in this case the employee ID. Now, this is not Some people will tell you that the one-to-one cardinality is not a good cardinality to design your model on, but I would say it depends, right? So you need to know the reasons why you have decided to leave a one-to-one cardinality. If you decide to do that, right, you just need to know why you are doing it. Some people will tell you, there are textbooks that will tell you that whenever you see a one-to-one cardinality, just go ahead and make that just one entity, right? I would not necessarily disagree with them, but I would just say it depends. Just make sure that you are judging each of your design on its merit. If you are in a situation where you have two entities and you have seen that between the two entities there's a one-to-one cardinality, before you rush to merge those two entities into one, look at the amount or the number of attributes in each entity and make sure you are not just creating a very wide entity when you combine them. So judge each design by its merits. Okay, so that's your one-to-one cardinality, and in this case it tells us where we are going to put the keys, right? We know that the primary key is going to be on both of those entities in our one-to-one cardinality. Okay, so that's your one-to-one cardinality. Let's move to our one-to-many. All right, so in the one-to-many, one thing that I want you to know is that if you look at this particular diagram right now without anybody telling you anything, you can see those two vertical bars on this side, so you know that the other entity is the one side, right? Just by looking at the diagram, you know that the order is the one side, and you see that on the other side, the other detail, right, there's a different symbol. Actually, if you look at this symbol very well, it actually looks like this, like three prongs going to connect to the other detail. Okay, why in the world did this do that? I didn't say you should do that. So what I'm talking about is on the other detail side, this is what you have, something like this. Okay, that's what connects to the other detail table. Okay, now this goes and connects to the one side. Now this side, the other detail side, is the many side, and you can see that the connector to the entity itself looks like the foot of a crow. So that's why it's called the crow's foot notation, just like we alluded to earlier on. So just note that in a one-to-many cardinality, the one side, you have already known how it's represented. The many side will be represented by that crow's foot. All right, so you know that that side is the many side. All right, so let's look at this relationship between these two entities. So you have the order on the one side, and you have the order detail on the many side. That's why it's a one-to-many. Right off the bat, understand that the one-to-many cardinality is the most desirable cardinality in relational database design. You always want to get your design in a one-to-many cardinality. You try your best to make sure that your cardinality is one-to-many, because that's the most desirable in relational database design. Okay, so what does it mean that two entities have a one-to-many cardinality? Again, let's test our theory as to how we determine that these two entities have a one-to-many. Remember, again, you have to go traverse the relationship on both sides. Okay, Again, yesterday we talked about a systematic approach to problem solving. You can see that we are applying the same steps to all our cardinality problems. So we are traversing the relationship on both ends. So in this case, our customer have told us, and we have documented it in the requirement document, and we know that one order, right, can contain more than one order detail. All right. If you've ever seen a receipt before, right, you know that an order can contain more than one order detail, right? Let's say you go to the store, you go into the store and you purchase as many things as you want to purchase. You have your basket. The whole of the basket can be termed as one order. The whole basket, your whole shopping cart, can be one order. Now, in that shopping cart, you have so many things. You can have fruits, you can have groceries, you can have detergents, you can have inside that same shopping cart. Now, that's the detail of the order. So that's exactly what we are saying here. In this business, we are told that one order, so we put one here, one order contains more than one order detail. All right, so again, if something is greater than one in the world of cardinality, we say it's many, right? So one order can contain more than one order detail, and I won't say more than one again. I'm going to now start saying many, but I just wanted to get us comfortable with knowing that anything that is greater than one is many. All right, so one order can contain many order detail, right? And one order detail, one thing, right, in that order detail can be associated with one order. Okay, so when we traversed it the other way, it's one to one. And what do we take? We take the highest on both sides. So one to many. All right, so that's how we determine that this particular relationship between order and order detail is a one to many cardinality. Okay, so now that we know that it's a one to many cardinality, what does it tell us? It tells us that the one side, the entity on the one side would have to be the primary key. Okay, and as we have seen here, the order, right, is on the one side, and that is why the primary key is on the order entity, like the order ID. So what does that mean for the second entity? Well, the second entity is the many. And so because the second entity is the many, this order ID primary key would have to be implemented in the second entity as the foreign key, right? And that is how we will be able to track your shopping cart with everything that is, every item that is inside it. Okay, because now we have that primary key on the one side and the foreign key on the many side. So now we know how the order is related to the order detail. If we see any item in the order, well, the order detail will have that same order ID as its foreign key, so we can track whatever is in our order to the details of that order. We can track your shopping cart with every item in the shopping cart. Okay, so you can see that your one-to-many cardinality is the most desirable cardinality in your relational design. So you should always strive to achieve a one-to-many cardinality. Any question? Okay, so finally we talk about the many-to-many, and you can see right away that you have the crow's foot on both sides of the many-to-many. All right, one thing you should know is we don't like many-to-many in database design, right? It's very tough to implement many-to-many cardinality, okay, because the complexity of many-to-many can not be adequately represented in our rows and columns. That's all that we have to represent anything. So when two entities have many-to-many, right, we have a problem in our hands. All right, but before we get there, our many-to-many relationship is also derived from the business rule. Okay, so let's go ahead and traverse. Now it depends on the business rule. Let's traverse our entities on both directions, right? So what does our requirement document say? Our requirement document says one student can take more than one course, which is many. One course can be taken by more than one student. That's the rule in this particular school. And again, we take the largest on both sides, which gives us our many-to-many. So now, based on that business rule, that's how we understand that the cardinality between the two entities, student and course, in this particular business is a one-to-many. In another business, the rules might be different and the cardinality might be different. So always judge each particular pair by that rule that you are talking about at that present moment. Okay, so you have a many-to-many cardinality. Now, in a many-to-many cardinality, the primary key of each of those tables or each of those entities will be their primary keys. It will be two different primary keys, right? So how would we relate? Think about your one-to-many. We were able to relate that shopping cart, right, on the one side with all the details in the shopping cart on the many side. We are able to relate it because we took the primary key of the one side into the to become the foreign key of the many side, right? So how would we do this in a many-to-many? Actually, it's almost impossible to do unless we intervene into the many-to-many. All right, so how do we intervene in the many-to-many to make sure that we are able to represent a many-to-many scenario in our database design? Because you would always have a situation where your entities have a many-to-many cardinality. So what do you do when faced with that situation? Well, it's kind of very easy. Anytime you have a many-to-many cardinality, all you have to do to resolve it is to turn the many-to-many, right, into two one-to-many. So from the many-to-many, you will make two one-to-many, right? So all you have to do is to just create another entity. We call that other entity, we call it the associative entity. Some people call it the bridge entity, right? Because as you have seen, it's bridging the many-to-many. So what we have done is we have students to student course, right? Instead of going straight from student to course, which is a many-to-many cardinality, we have students to student course. Right now we have a one-to-many, which we like, right? A one to many. Now that's one to many. And then from student course all the way to course, we have another one to many. So we now have two one to many from our one many to many. Because we now have two one to many, we are able to represent this in our database, because remember, the one to many is always our desired cardinality. Okay, so what does this mean for implementation? Now you can see that in our many to many world, you had the primary key in the student entity, you have the primary key in the course entity. But because we have introduced an associative entity to the mix, we have to make sure that we combine the primary key of the two entities that we had in the many to many situation in the associative table. That way you would have a composite primary key. It will be a combination of both primary keys, right? A composite primary key is what you end up with when you solve the many to many situation. Okay, so in this case of a student and a course, our student and our course can be bridged by a student course entity. Okay, and in that entity we have the student and the course interacting together. We can have a grade attribute and any other attributes that actually make sense in that scenario. So in a nutshell, we have gone through the cardinality and the implications of cardinality, right? So now in our design, right, because we have done this exercise for every pair of entities that we have in our logical design, some of them would have relationships, some of them will not. The ones that don't have relationships, they are fine. We don't have to have any cardinalities between them. But once your business rules tells you that two entities are related, then you have to determine what the cardinality is. And in determining what the cardinality is, what you want to do really is to make sure that you can break down the cardinality into as many, now I'm using that word in English now, into as much one to many as possible. That's actually the goal of your cardinality. You want to make sure that those entities, if they are one to many naturally, then you are fine. But at the point where you begin to see them as many to many, then you have to break them down into two one to many. And then that will tell you where you should put your primary key and where your foreign keys will go to, in order to be able to implement that relationship. Any question? Okay, so now we've made progress. We know what cardinality is. So now with cardinality tucked securely into our toolbox, we have something new to add to our toolbox. Let's turn our attention to another important design concept: normalization. Okay. In the logical design phase, normalization is the mathematical method of evaluating the relational quality of the data model. What this means is that normalization is an objective way to ensure that we do not store redundant data in our databases, and as such, it ensures that the database remains consistent. Okay? So up till now, everything we have been doing is really subjective, right? We are basing our hopes on the fact that our business users or our clients will give us their best information. We are trying to see how we can come up with a conceptual design, a logical design, a physical prototype, and then we looked at the relationships and we come up with cardinality, right? But now we are going to use a tool that can tell us objectively that our data model, that we can use to evaluate the relational quality of our data model. Okay, and the aim of normalization is to make sure that we do not store redundant data. Okay, so now the question is, what is redundant data? Okay, that's what the question is. What do we mean by redundant data? This is what I'm talking about. What does it mean to say that we want to redundant? What does it mean to say that we want to avoid storing redundant data in our database? Because that's what our normalization is going to help us achieve. Okay? To explain redundant data, I will need some visual. Okay? That's one of the things that it's better seen than explained. Alright? So, to explain redundant data, I would like you to take a look at the slide that we have here. In this slide, you see the data model of a fictitious retailer. The data model shows three entities used for sales and fulfillment. So you have the customer entity, you have the shipping entity, and then you have the sales entity. We see the customer details for two customers, Jane and Paul. We also see what they purchased and when it was shipped. What they purchased in the sales entity and when it was shipped in the shipping entity. Okay? Now, we see that when Jane purchased the 34 quantity for $40, we can trace the fact that Jane, the customer that lives on Wolf Street, purchased 34 of some gizmo for $40. And we know, based on the first name and the last name, that it was shipped on this day and it is due to be delivered on this date. Okay, so we can follow that trend from what we have here. Now, just assume that Jane's last name changed to, let's say, Smith. Okay, so now Jane is not Jane Doe anymore, but now Jane is Jane Smith. And we have rightly come here to the customer entity to change that name. Okay, now we have a problem, because now Jane is Jane Smith in our customer entity, but Jane is still Jane Doe in our shipping entity, and Jane is still Jane Doe in our sales entity. So now we don't know which is which. So what this means is that we would need to change or to use the database term update. That's the database term for change something. All right. We will need to change or update Jane's information in all the tables or in all the entities where our name data is stored. In this case, we will need to come to the shipping entity or the shipping table and change Jane's name to Smith here. And we will now need to come to the sales entity and change our name also, our last name, to Smith. Okay? When a data point, in this case, the last name, any data point, right? The data point we are talking about in this case is the last name. But when any data point is stored in more than one table or stored in more than one entity, we say that that data is redundant. To make any change to data that is stored redundantly, you will need to track all the fields where you have that data point stored. In our case, we will need to track all the tables where we store last name and change that in all that table. Okay? Now you might say, oh, big deal. It's just 3 tables. Okay? It's 3 tables in this example. Think about enterprises that have hundreds, sometimes thousands of tables. You will begin to see how this can be a problem in tracking changes made to a single data point. Let's say our organization had 100 tables and we had to change the last name in 100 places. You can see that the possibility of us leaving one out and disjoining the data, making the data not tell us a complete story, that probability is higher because we have stored that particular data point in more than one place. Does that make sense? So you will begin to see how this can be a problem in tracking changes made to that single data point. When you store the same data point in more than one entity or table, updates to that data point must be tracked in every entity that the data point is stored. So how do we avoid storing redundant data? Right? That's where normalization comes in. So now you have seen the problem. Okay? So normalization helps you avoid making updates in so many places by ensuring that you do not store redundant data. So if anybody asks you, might be in an interview setting, might be in just normal conversation, if anybody asks you, what is normalization? What would you say? So let me take that again. So let's forget. And the reason I'm saying this is if you remember the story, you would know how to put these things in your own words, right? So let's assume that we have 100 tables in our database and we have stored the last name in 100 places. And then we forget to change just one place. We've changed 99 places and we forgot the shipping. We forgot the shipping to change Jane's name to Smith, right? Then one day, Jane calls our customer service and says, that gizmo that I bought, I never got it. And they were like, the customer service was, Oh, so what's your name? That's no problem. We can figure that out for you. What's your name? And Jane, the newly married, wants to use her last name. She goes ahead without thinking about it. She just says, yeah, my name is Jane Smith. And the poor person in customer service writes the query to look for Jane Smith in the shipping table, and she doesn't find Jane Smith. Because really, there's no Jane Smith in the table. There's Jane Doe. Because we have stored that data point in so many places, right? The possibility of us forgetting to update it in one place is high. And forgetting to update it in one place is a big business risk. Which is why we always want our data, or storing our data, to not be redundant. Let me take that again, because I use so many negatives there. We always do not want, I'm doing it again, we do not want to store redundant data. Whatever we do in database designing, we never want to store redundant data. And we know what redundant data is. Redundant data is when you store a single data point in more than one place. That's you have created redundancy. Okay? So, normalization helps you avoid making updates in so many places by ensuring you do not store redundant data. This makes your database consistent. Okay? You can see in our case, when we forgot to update the shipping table, our database is not consistent. We can't get the answer that we should be getting from our database because of that particular redundancy. All right. So one thing that normalization does is to avoid making updates in so many places, because we are sure that we do not even store redundant data in the first place. Okay. So the purpose of normalization is to reduce or eliminate update anomalies that can occur when the same data point is stored in multiple locations within the database. So normalization should be seen as a tool to help reduce update anomalies, as we have stated earlier, by eliminating redundant data. We have seen that redundant data has the risk of making our data inconsistent. And then we are actually wasting storage resources by storing a data point in multiple places. Okay? So now we know that we have a tool in our pockets called normalization that would help us eliminate storing redundant data. Any question? I promised that this class wasn't going to be long, so I've just introduced normalization. Now we know what normalization is. Now we know what problem normalization will solve. And now we know why it is important that normalization solves that problem. We don't want inconsistencies in our database. We don't want 99 tables to say Jane Smith and one table to say Jane Doe. That is inconsistent data. Okay? So, now that we know that we have a tool, in our next class, we are going to start using this tool, right, in order to make sure that our design is free of redundant data. Any question?